Hi, I'm Kaitlin Krejcik, a student in Dr. Mitchell's remote sensing course at the University of Maryland. In this video, I'll be discussing the basics of remote sensing and how we use them in our semester project. Remote sensing is gathering information on a topic without making any direct physical contact. There are two types of remote sensing, active and passive. Passive remote sensing uses naturally occurring radiation, like sunlight, while active remote sensing transmits its own radiation, like sound or light waves. A camera with flash would be active, while a camera without flash would be passive remote sensing. The purpose of this project is to design, construct, and implement a LiDAR system capable of mapping a unique target on campus. Because a big part of the class was becoming familiar with Python and related processing platforms, we all used the Raspberry Pi for computing in the field. Most students chose to use Dr. Mitchell's design to 3D print a mount for their systems. Here's a look at my LiDAR.
I 3D printed the mount from the files Dr. Mitchell posted, and I chose to do it in two pieces so that it was easier for TerrapinWorks. And then I hot glued it and I attached it to my tripod using the connecting plate. Next, I attached the Arduino in its slot using zip ties. And the Arduino is currently powered by USB to my computer, and that's also how the code is transmitted to it to run the laser. The laser is connected to ground and 5 volts on the digital end of the Arduino, and it's in this slot right here. And next I attached my Raspberry Pi and camera to the top end of the mount, and I used tape for the Pi and zip ties and string for the camera. I wanted to make sure that the camera was really secure so that it didn't move, so that's the reason for both string and the zip tie. Lastly, the Pi is connected to my computer via Ethernet so that I can plug it in, and it's also connected to power.
In our first assignment using OpenCV, we ran a code that would detect a colored circle. In this video, green circles are detected and tracked. This assignment opened the door for the next one, where we used OpenCV to track the coordinates of a green point laser in the frame. This was our first real LiDAR sensor. Next, we calibrated our final LiDAR sensor indoors, and then used it to map a simple target as a test. I chose to map this chair with a stuffed panda.
First, I copied the images from the Pi onto a thumb drive and onto my computer. Then, I copied the folder into the correct PyCharm projects folder. I changed the file name in the code to match the file that contains my images. And then I went down here and made a name for the text file that the code will output. Then I went back to the top and changed these lower color values that I found using the color picker code for my inside setup. Now I'll run the code and we can look at the initial output. Here you can see the image that the PyCharm code outputted. At the top here you can see the data point that I took. That was just the wall, and then as you go down you can see elements of the chair and the animal popping out. And it's not very detailed, but you can definitely tell. Here's the back of the chair, here's the panda bear, here's some of the seat and some of the bottom of the chair that I made a point of taking data for.
Now I'll talk about my target, which is the Maryland flag panel located at the main entrance to Maryland Stadium. I wanted to map a unique target, and I knew that nobody had mapped the panel in the class's first semester. It has a recognizable pattern that is shown by large cutouts, which are great for LiDAR mapping. I also chose this target because the Maryland flag is an important symbol and source of pride for the university. In addition, since I've lived on North Campus all 4 years, this particular panel welcomes me back to campus every time I return. Now we'll get to what I did to collect my data.
As you can see in these first two photos, I arrived at my target right around dusk. I was kind of excited and got there a little too early, so I had to wait a little bit for it to get darker out. However, as you'll see in the next part of the video, as my surroundings got darker, the background behind my target had more contrast. It was a tough balance to strike, and I do think it affected my data. The next part of the video is a time lapse that I took while I was taking data. My method here was similar to the way I collected the data in my room. After setting up my LiDAR system outside, I used the data collection file to take data from different angles. I wanted to capture the main features like all of the shapes included in the flag panel. So the important parts to capture are around the top, middle, and bottom bars because they show the transitions in the flag. Hi, I'm here at my target, which is the Maryland flag panel. The surrounding area is the circle by Denton and C-SPAC, and so this panel is right at the top of the football stadium. It's on the 3rd story of the parking garage, and as you can see over here, there's a lot of lighting because of the garage. So what I did was I draped a blanket behind my target because before, when I was taking data, there was a lot of light coming through these holes in the panel, and it was making the data processing pretty hard because I couldn't do much editing because of the shape of it and the fact that it was coming through the back of the panel. So this is what I did just to give a darker background for that.
Now I've collected all my data and we can see how I processed it. I was lucky in that my target didn't require data from different angles because it's just a flat panel. To account for the size of the panel, I just took 2 viewpoints, one from the left and one from the right. Once I had imported both text file outputs from PyCharm into MATLAB, I translated one side by trial and error until the majority of the points from the 2 viewpoints were flushed with each other. I filtered the points in MATLAB based on their position to get this cloud. Many of the points that I wanted to filter out were those from the returns off of the blanket, which was several inches away from the back of the panel. Unfortunately, because of some irregularities in my data collection, not all of my desired points are completely flat like the panel. This meant that I couldn't filter out all of the undesired points without also removing some of the points that I needed in the point cloud. This 3D point cloud is pretty representative of the actual panel. The main elements of both coats of arms are distinguishable. The cross of the Crossland coat of arms on the top left and bottom right, and the vertical bars of the Calvert coat of arms on the top right and bottom left. My next step was creating the mesh from my 3D point cloud. I started out using MeshLab, and even with the given instructions and some YouTube tutorials, I felt like there was a lot I was missing in using the program. Once I saw what a big mess this mesh turned out to be, I reached out to my classmates to see if they were having any luck. Several people reported success with Cloud Compare, so I decided to give it a try. One benefit to using Cloud Compare was that it actually allows you to clean up your point cloud by taking out individual or groups of points. So after I imported all of my data into Cloud Compare from the text file, I was able to select the points that I didn't want to include in the final point cloud. This was really helpful to me because, as I mentioned previously, my MATLAB filters had limits to their effectiveness. Taking out the noise and returns from the blanket gave me a much cleaner point cloud, and it allowed me to construct this mesh. It's clearly much better than my first attempt in MeshLab. As we rotate the mesh, you can see that there are some points on the back that are a little overgrown, but the main features of the flag that I wanted to show are preserved. Overall, I'm pretty happy with my final product, and I've really enjoyed spending the semester working on such a unique project. I hope you've enjoyed this video. Thanks for watching.